Welcome to our lesson on Chapter 1.4, Inverse Functions. Now, this section is incredibly important as we move forward because although we can do transformations of any type of function, transformations, as I said in the past, aren't always the most important thing in the world. When they're useful, they're great, but a lot of the time we don't care that much about it. However, inverses are going to be one of those things that come back again and again and again. And it's really important to understand what an inverse is because it's a very simple idea. And it's going to allow us to understand, like once we understand how a function works, we can understand how its inverse works by understanding the ideas about what makes an inverse function an inverse function. So the very simplest way to look at an inverse function is an inverse function is what you get if you switch the x and the y in an equation and then rearrange that equation and solve for y. I guess another way you could think about it would be if you just took an equation and solved for x and looked at that as a function. But because we're so used to our independent axis being our y's, we want to switch those x's and y's first and then put it into y equals form. We can graph any function, or sorry, if we have a graph of a function, we can create the inverse of that function by switching the x and the y columns if we have the data table for that graph. And what that also means is graphically, if I were to just look at the function, I'm going to see a reflection in the line y equals x, and we'll see that in our example in just a few moments. If I'm just switching my x and my y coordinates, what that means is that the mapping rule is to, like I said, if we have that data table, we just switch the two columns. We switch the x's to the y's and the y's to the x's. So a little bit of notation. An inverse of a function is represented by one of two ways. And the first way here is, as I said a few seconds ago, isn't really the way we like to do it. We could write that function as x equals a function of y. But the way we usually do it is it looks like it's f to the negative first power. It's not f to the negative first power. It's f inverse of x. And I'm just going to open up the 84 emulator here for a second because there's a button on the 84 calculator, or on most calculators really, that we often look at and we talk about it as being the inverse button. And that's this little button right below math. Above the squared button. We usually talk about that as the inverse. And what it does, as you can clearly see, is it just does 1 over whatever the value was. So it is raising that value to the negative first power. Those of you who saw some matrices or remember what we did with matrices, when we took the inverse of a matrix, we used that button. We talked about then that that button is really the inverse operation. When we just put a number in like I did just a second ago there with that 8, the calculator takes it as sort of 1 times 8. And so the inverse of that would be dividing by 8 is kind of what's happening there. So it's really, really important that we understand that f to the negative 1 is the inverse of something. Later in the semester, we're going to see inverse trig functions. And this f to the negative 1 represents the inverse of the function f, not 1 over f, or not f to the negative first power. And that's about the 4th time I've said that in the last 3 minutes. So hopefully that represents how important it is to understand that we are now using this, what looks like an exponent of negative 1, as the inverse of a function, but we're not actually raising it to the negative first exponent. So one thing that's really interesting about inverse, or taking the inverse of a function, is that the inverse of a function is not necessarily a function itself. So if an inverse doesn't, how should I say this? If the inverse function doesn't pass a vertical line test, then the inverse function is no longer a function. Even though we tend to still talk about it being a function if the original function was a function. we can sort of flip the vertical line test on its head and say, if I have a function that passes, let's call it a horizontal line test, and we'll pretend that's a nice cubic, so there's no little bumps in there. If it passes that horizontal line test, then the inverse of that function will be a function as well. But why don't we do the example before we get too far into that? And once we graph the function that we have in the example, it'll probably make a little bit more sense. Okay, so let's look at what we're going to do here. So I have the function y equals x squared. I'm going to fill in the data table. I'm going to graph my function. Then I'm going to graph the inverse by creating a table for the inverse. Well, so this is pretty easy, just a regular quadratic. Oh, I'm going to switch that to black, actually, before we go. We're going to color code things a little bit here. So -2 squared is 4, -1 squared is 1, 0, 1, 4. So nothing overly exciting happening here, is there? I'm just going to put those points in, and I will sketch my quadratic. Okay, there we go. So now let's make a table where my x's and my y's switch. So I get 4, 1, 0, 1, 4. It kind of looks weird. And if you're thinking sort of the Math 10 exam type question where we get the data table and we're trying to figure out if it's a function or not, the fact that we have two numbers that are in the x column, and I should be clear here, even though I labeled those how we're switching them, when I'm going to graph them, this is my x's now, this is my y's. I have switched these two columns to create my new data table. So I get -2, -1, 0, 1, 2. Okay, so let's graph this. So I have one at the point 4, -2. I have one at the point 1, -1. I have 0, 0. I have 1, 1. So that point's right on top of the other function. And then I have 4, 2. And so when I get that, you're going to see I basically have, it's not drawn horribly well, but you can see that I have a quadratic on its side is what it looks like. And if you're able, I'll try not to draw too much on this, but if you're able to picture it, you can see that these points have been flipped right over that line y equals x. So I can see visually that the line segments that connect those pairs of points are perpendicular to the line y equals x, and it passes equidistance in between them, right? So I don't know that you'd want to, but if you calculated the distances of those blue arrows, you would see that the line y equals x passes right through the middle of it. Now, we'll switch to green. Now, actually, let's just draw a line on here for a second. If I draw a line, oh, that did not do what I wanted to do. One moment. Oh, I'm still on the pencil there. Okay, so I just drew a vertical line, and you'll notice if I drag this basically anywhere except if it's tangent to the curve right here. If you don't know what tangent to a curve is, we can talk about it more in physics or in calculus next semester. But I can see wherever I put that thing, I get 2 points. That tells me that the inverse of the equation y equals x squared is not a function itself. Now, we're going to do this algebraically, and then I'm going to show you how we can make the inverse by doing a pair of functions, actually. Okay, so let's try. Oops. Okay, so algebraically, we had y equals x squared. We're going to swap the x and the y. So I get x equals y squared. I'm just going to flip this around because we tend to like the thing that we're solving for on the left-hand side. You don't need to do that if you don't want to. Now, don't forget, when we take the square root of something, we need to take both the positive and the negative root, right? The square root of 9 is positive 3 or negative 3. We haven't always cared about the difference between the roots. We definitely care about the difference between the roots now. Now, I can separate that function, and I can use two functions to create the inverse function. Okay, so the inverse of y equals x squared is made up of two functions. One is the positive square root of x, and the other is the negative square root of x. And I think you've seen piecewise functions before. It's just a function that's made up of multiple functions. A lot of times you might have, over to the right out here, you might have a domain restriction. We don't have a domain restriction. Well, I mean, for both of those functions, x has to be greater than 0, but that's because the range of the original function was y is greater than or equal to 0. All right, so now that we've seen what an inverse is, how to create an inverse, we can do it from a table, we can do it from a graph, we can do it algebraically. Let's take a look at one more example here. So we're going to do the function f of x equals x squared plus 3. We want to determine the inverse of f of x is the inverse of function. It's not spelled correctly. Fix that. If not, how could I restrict the domain so that the inverse would be a function? And then we'll have to think a little bit about what that means. So let's do this the easy way first. Let's do it algebraically. So I've got y equals x squared plus 3. I'm going to switch the x and the y. So I get, we'll now get that y squared by itself. So I'm going to subtract 3 from both sides, and I'm just flopping sides of the equation as well. Take the square root, and I get positive or negative the square root of x minus 3. Okay, so that's two functions, right? Now, if I graph these, and we may not know what square root functions look like yet because we haven't really done anything with them. So let's jump to the calculator, or you could go to Desmos if you want to. And I'm going to do square root of x minus 3. And then I'll also do negative square root of x minus 3. And just for the fun of it, let's throw in the line y equals x and the line x squared plus 3. So we'll graph everything to start with, and maybe we'll come back and dump some of that. Now, one of the problems here, because I went to standard zoom and the screen's not a square, you can see that it's been squished a little bit, so it's kind of hard to tell graphically that those are inverses of each other, but we can at least get the idea of what that square root function looks like. So the blue one, that was our positive root x minus 3, and the red one is the negative root x minus 3. And it looks kind of exactly like what you would expect. The y-intercept of our original function is at 0, 3. And when we switch those coordinates, that takes us to the x-intercept of 3, 0 for our inverse functions. Now, if I look at just my red or my blue line, those are functions in themselves. So I'd have to think about what would happen, or how could I restrict the domain of this pink function of that y equals x squared plus 3 in order to create one of those? Well, I can do one of two things. So I've got my quadratic, and if I want to get this function, when I'm mapping it, or I'm looking at that reflection across the line, y equals x, I'm just looking at that part of the original function. So I could say for f of x equals, or here, let's, no, this will be okay, x squared plus 3. And I'm going to put a domain restriction on there. I'm going to say x is greater or equal to, to 0. Then the inverse is going to give me that positive x minus 3. My other option there, if I wanted to get that bottom part of the function, I could say for f of x equals x squared plus 3 when x is less than or equal to 0. So I can see how this part is mapping down onto that red function. Then the inverse function is going to be negative the square root of x minus 3. So I've actually done a little bit more than I was asked to do in that example. I've gone through and I've actually come up with two different domain restrictions such that the inverse then becomes a function, right? Because my problem, of course, is vertical line test, right? I put a vertical line test in there and that fails. But if I only have either the blue function or the red function, then I'm okay. All right, there are two more functions for you guys to determine the inverses of, and then we can talk about any issues that you may have had with any of these in our next class. Good luck with those.